Yeah, that's good. Okay, great. Well, okay, so I want to talk to you a little bit about sort of a related theme, actually, about sediment supply and erosion on shore and its effect on subsidence in the rifted margins. And particularly, I'm going to take you to South China Sea. Oops. Let's see, there we go. So as you all know, there's an expectation about the type of subsidence that one might expect on a rifted margin based on the degree of extension. And, simple models like uniform pure shear extension make predictions about the amount of substance you would expect in the basement through time based on the amount of extension. Of course, that's a very simple model, and we do know that there are a variety of reasons why that's not always true, that there are different ways of accommodating the strain in the upper, lower crust and the mantle lithosphere that make a difference to the local subsidence. And of course, also models like this, simple shear systems, don't subside in that very simple way. In places where we remove a lot of the mantle lithosphere compared to the crust, you get departures from that very simplistic model. So what I'm trying to do here is to look a little bit about how the South China Sea margin subsided through time, and particularly to look at this idea. So I've got an old model now from Neil Driscoll, Gary Kana, this concept of the upper plate paradox, and that is that passive margins often seem to subside rather more than one would expect based on the degree of their normal faulting. And particularly what I'm going to look at is the amount of extra subsidence and when that happens. So this is my friend South China Sea, and mostly we're going to be talking about this northern area offshore southern China, offshore essentially Hong Kong, Guangzhou, and more importantly, the mouth of the Pearl River. So what sort of a rift is this? It's sort of like a wide sort of rift, weak lithosphere, more similar, say, to the Basin and Range than, say, to East Africa, as we were reading about earlier. And I'm using here this subsidence software, modeling software, the flexural cantilever model from Egan et al., written by Alan Roberts and Nick Kuznir. So this is pretty old work for me now, but just briefly speaking, essentially, if you look at the rifted margin offshore southern China, when you look at the faults, which you can see on the seismic profiles, they make a prediction about what the margin would look like today, and essentially there's not enough substance here. There's a lot more in the reality, particularly in the post-rift sequence here. And at the time, we ascribed that to preferential thinning of the lower crust, ductile flow in the lower crust, reflecting the very weak nature of the lithosphere here. And we knew that this wasn't just a simple shear sort of effect because of what we saw on the conjugate margin here in the dangerous grounds offshore Borneo and Palawan. We saw a similar sort of situation where the model predicts moderate subsidence and the reality is much greater. And then here, in fact, actually, the preferential thinning of the lower crust is even greater than what one would expect. So we were wondering that in order to account for this, we have to have preferential thinning on both margins. And since you can't flow the crust sort of under one another, the expectation was that this was a result of lower crust flowing towards the newly opening basin, reflecting the isostatic potential of the margins. So the question was essentially, well, when does this lower crust flow occur? The assumption was that it was during the rifting process. But this is not always necessarily the case. So next door, just to the west here in the Yingahai Songhong Basin offshore the Red River Delta, very deep basin, and we saw here there's a very significant wedge of sediment is deposited here, the blue here during the Pleistocene, thickening very substantially towards the south. And when we looked at trying to look at the substance analysis of individual wells in this basin, we saw that there was an acceleration in the last 5 million years or so that got stronger and stronger towards the southern end of the basin, particularly where the sediment, the Pleistocene thickness was the greatest. And we wondered if there might be a link there. So looking offshore southern China here, there is a very deep basin here called the Baiyun Sag. It's extremely deep, about 14 kilometers deep. And we wondered, well, how did it get to be so deep and what caused it to do that? And it is interesting to note that most of the we know that the faulting here stops about 20 to 23 million years ago. So when we attempted a backstripping analysis here, essentially you end up with this very deep basin here. And essentially, the way, given the age of it, this essentially predicts that we should have essentially infinite extension under that. So this begs the question of, well, why does the breakup, this is the true continent ocean boundary. So if the breakup happens over here, well, essentially, why didn't it happen over here? And the answer to that may be when that extension occurred. So we got a clue from this by, well, I mentioned the fact about essentially that the amount of upper crustal extension isn't that high, and most of it ends, you see, after about 24 million years ago. So if you look at this figure down here on the bottom, this is the black vertical lines here show you the depth to basement through time, sediment unloaded depth to basement through time. And what you can see is that there is an acceleration here between about 30 and about 20 million years, where the basement undergoes a significant amount of tectonic substance. So this isn't related to sediment loading per se, because that's already been accounted for in the unloading process. But this blue shaded time is also one of elevated sedimentation in the basin itself. So based on the earlier substance rates in the early part of the rift, you would expect the depth to basement today to be unloaded depth to be about 3.5 to 4 kilometers. And the reality is it's almost a kilometer deeper than that. So the suggestion here is that the accelerated substance occurs after the end of brittle faulting, but during the time of elevated sedimentation. And in fact, 3D mapping of this area offshore by people with access to better seismic than me shows that there is this pulse of sediment entering the basin, presumably from the Pearl River around that sort of time, particularly after around 20 million years. And so this was modeled by Sascha Brunner. Essentially, what we tried to do was to look at the different viscosities of the lower crust. And we see that when we load the basin, that we can get appreciable amounts of lower crustal flow if the viscosity is low enough, as we believed it would be. And essentially, in a more detailed model, we showed that the extended margin of southern China here during the rifting, if we took that little part of the margin and loaded it down with sediment, and we tried to use use the appropriate amount of sediment based on our seismic surveys, that you can see here that there is this tendency of the lower crust to flow away from the depot center. And so our belief was that that accelerated phase of subsidence, as it was in Yingahai, is related to ductile lower crustal flow that's being induced by the sediment loading. So not in the normal type of sediment loading, but sediment loading that essentially thins the crystalline crust. So the idea is that Cenozoic erosion on shore, modulated by the Asian monsoon and by drainage evolution, is removing material here, unloading the onshore and dumping that load into the offshore, which is then triggering ductile middle crustal flow of this, as shown in this cartoon. So, of course, what that really means is that this subsidence in the offshore is actually partly modulated by the strength of the Asian monsoon rainfall, and also by the drainage evolution, which is quite complicated in this part of the world. So we do know that there are these big rivers in southeast Tibet, some of which may have connected through to the South China Sea in the past, prior to its disruption due to Tibetan plateau uplift. And that means that the drainage reorganization is going to affect the degree of lower crustal flow in the offshore margin. So particularly, of course, there's been this long argument about drainage capture around southeast Tibet. And this has affected, of course, in our case, the Mekong River, but also to a lesser extent, the Pearl. The Pearl is not so caught up in this problem. We do know from data in the offshore, in the southwestern part of the South China Sea, that the Mekong may be relatively young. So this is a whole series of proxies going back to 18 million years ago. I particularly draw your attention here to neodymium isotopes, which are a good provenance proxy. And you can see it's pretty stable back to about 8 million years ago. A little crazy point there, but pretty stable. Whereas before, it's quite variable. And this was used to argue by Liu et al. That the Mekong has been in its present location about 8 million years. You can see this in a cross plot too, where the data in the older part of the margin is more displaced towards these oceanic end members, Luzon, Palawan, and so on, and that it stabilizes and becomes more related to Indochina in the more recent past.
You have 10 minutes now, okay?
Okay, I'll wrap up in a couple of minutes here now.
No problem.
So you can see that this is broadly consistent with what we see in the seismic, that the big cliniform facets of the Mekong shelf. This is the edge of the Sunda shelf here offshore of southern Vietnam, that a lot of those are essentially Pliocene and younger. So it's a relatively young delta system. It's probably evolved actually from the Gulf of Thailand. The situation is a little bit different in the north, and that's why the timing of lower crustal flow may be different in different parts of South China Sea. In this region, this offshore is mostly being supplied, well, recently from Taiwan, but before that, mostly from the Pearl River. And so we were able to get at this a little bit through recent drill sites from IODP, where we were able to look at the Sin Rift, both at these two sites that are separated by a structural high. And essentially, this is our attempts to look at the zircons. This was published quite recently in EPSL. And maybe not surprisingly, we see a very simple pattern in the oldest part of the sequence here that gets more and more complex as we go up through time, and particularly in the middle and latter part of the Oligocene. So it looks like the loading of the margin doesn't really occur seriously because of Pearl River sediment derivation until a bigger Pearl River is established, starting essentially in the upper Oligocene. You could see this a bit, the provenance evolution here in this multi-dimensional scalar diagram, where the young part of the margin over here on the left is quite different from the two separated and independent Sin Rift sequences and the two IODP sites. So we had isolated basins with local sources at the early part of the rift, then breaking up and becoming amalgamated later on. So with the latter part of the margin has sediments that are quite similar to the modern Pearl River. Anyway, so I'd like to wrap up at that point, and if you have any questions, I'll be happy to try and answer them. Thank you.
Thanks a lot. We have a little time for some questions. So I see that Mohammed was asking which software is used for backstripping. So we can start with that.
The two-dimensional backstripping was done by FlexDComp from Badley Geosciences. The 1D backstripping, I think I did that with this. It doesn't even work anymore. It's this Macintosh program, Backstrip. It doesn't work with the more recent versions of Mac iOS, Mac operating system. The newer one is awful, in my opinion.